semester. And today we have Elad Levintal from BGU University. You're sitting in Slovakia, right?
Yes.
And he's a senior lecturer, and his group focuses on air, soil, water interactions and vadozone biogeochemical transformations using data from open source do-it-yourself sensors arrays that we will hear what it is in a few minutes. And before that, he did his postdoc at UC Davis and his PhD in BGU in hydrology.
Yeah.
So please take it.
Thanks. So first of all, I'm very happy to be here. I did my bachelor degree here in environmental studies. So I'm really happy to be here again. And this seminar will be maybe a bit different than what you're used to here. We'll talk more about the method we're using, developing, or a type of method, which is gaining more scope in the world. And I hope that maybe it will open new ideas for you. And in the end, I will talk also a bit in depth on some of our research in our lab. I'm a new researcher. I started like a year and a half ago. So I will present some projects that are in the initiation stage and some projects that are more solid. Okay. So first a bit about the place I'm coming from. So I'm living in Reshet Ben-Gurion, it's Boker, also where there is a faculty of Ben-Gurion University. In the faculty we have we have 3 departments. I'm in the Zuckerberg Institute for Water Research. We have hydrologists, water contamination, and different topics. And we are about 70 researchers and 250 students, roughly half international and Israelis. Only advanced degrees from master, PhD, and postdocs. Okay, so what is open source hardware? Because I know it's not a common term. So essentially, it's hardware whose design is made publicly available. You can study, you can duplicate it, you can do it with it whatever you want. You don't have to pay anyone in most cases. Very similar to the concept of open source software, like Linux, if you know, but on the hardware side. Open source hardware is a newer field compared to software. 2 main examples that are maybe some of you heard of. One is the Raspberry Pi, like a microcomputer, in about $30, $50, $40, which the hardware is not open source, but the system is. And Arduino, which is a very simple microcontroller, like electronics, very low cost. With a few additional items, you can build your own data logger, which can cost like $50 instead of $5,000. So these are 2 examples, the common one. Why using open source hardware? Why do I want to lower the cost of our sensors, our data loggers? So if my sensor is cheaper, I can install more sensors in the same price, in the same budget I have, compared to a commercial sensor. And I can build my customized solutions. When you're buying a sensor or a device from a commercial company, usually it's very hard to modify it. But here we can build our own solutions according to our own specific research needs. And it's all about the research, at least for me. We're not like developing products to sell them cheaper. We're developing sensors, hardware, which are cheaper, because then we can implement more of them in our research. So low cost of sensors, and usually with similar accuracy, because it's all about the accuracy, precision, and so on. We're looking for sensors that are research grade. Then I have the ability to install more sensors. We're talking about a 10% ratio, meaning if my local sensor is 10% of the commercial sensor, I will try to develop it. If it's like 60% of the sensor, usually I will not go into it because it's not cheap enough for us. And if I have more sensor, I can better understand what is happening. For example, if I'm taking a CO2 sensor, if the CO2 sensor the cost is 1,000 shekels, and this is my budget, I will buy one, I will put it in the middle of the class. But if now my sensor costs 100 shekels and I have 10 sensors, so I'll put one in the middle of the class, one next to the door, maybe 2 next to the windows, maybe different heights in the classroom. So you can understand that with 10 sensors, I can really understand what is happening, or better understand compared to one sensor in the middle of the class. So that's the concept. Where do I buy this hardware? Not the regular companies we are getting our official quotes. Amazon, eBay, AliExpress. And these are examples for Arduino board, which again is the most common board from which we can buy. We can develop our own data loggers. It's a bit hard to see, but this is $20, this is $14. It's exactly the same hardware, but they copied their design, and it's completely okay because it's open source. So they copied the design of the Arduino company, which is the first one to develop this type of boards. They're selling it cheaper, and that's completely okay because that's the philosophy. It's open source. And the sensors, we can buy them from, again, whatever website we want. But a few main companies that sell good enough sensors for our cause. One of them, for example, is the Adafruit. It's a company based in New York. They are selling different sensors. In this case, it's a temperature, humidity, pressure sensor in $20. And it's completely research grade. And with this sensor, together with the data logger, I can measure what is happening in the atmosphere. Only these parameters, of course, but very, very cheap compared to the traditional solutions we are using. And most of us are using, for example, for a data logger, Campbell Scientific data loggers, which are very, very expensive. Of course, they can do more than this type of data loggers, but for most of us, it's a complete overkill and with too many features that usually we don't need. And the beauty when you're buying this type of hardware, that the philosophy is open source and teaching. It's not led by the academy, it's led by what is called the maker community. So when someone is selling their product, they're also providing a complete do-it-yourself guide with videos, with tutorials, even explaining how to solder if you have no clue how to connect things. So mainly you need motivation and you can start building your own devices. And time, of course. And now I will show, after explaining a bit about what is open source hardware and sensors, I will try to give a few examples of how I use this type of sensors through my studies, through my PhD, and now in my lab. The first system is the EE greenhouse with collaboration with Oregon State University. We developed a system of several sensors in this white box, which you can see it here in a greenhouse. The box is moving on a robotic arm in the greenhouse. And while it's moving in the greenhouse, we can measure different parameters of the atmosphere in the greenhouse. For example, CO2, temperature, relative humidity. Everything is being logged on an SD card, but also being sent to a server and being uploaded to the web. Now, you have solutions already around 10, 20, 30 years that can do similar things. But you don't have solutions that are in the scale of a few $100s to measure what is happening in a greenhouse. And why is it important? Because if it's a few hundreds of dollars, then we can build more of these, we can install in different greenhouses, we can do better studies. So this is the first example. And once it's successful, we also publish it in relevant journals with a complete do-it-yourself guide. So if you want to try and tackle this and also build it in your own lab, you can do it. And if you have problems, you can send us emails, and everything is very documented to allow other people to build it and duplicate it. Another system I developed in my postdoc at UC Davis, most of my research was on nitrate transport in the value zone. And we had problems that most of our experiments were in agricultural fields, but then if you're starting to put cables on the ground, the farmer usually is saying, no, don't put it in my field because I need to move with machinery. So we developed a system that all the sensors are underground, connected to what we call an underground node. And in this node, we have low-cost electronics that is sending all the signals wirelessly through the soil to an above-ground hub. And by that, we don't have cables on the ground, and we can work in fields that we couldn't work before. Now, I'm not an engineer, but because everything was online with tutorials, we could develop this system, start working with wireless communication, and provide our own solution, although we are not with this specific field. Now, this is a hybrid model because this is low cost, but the sensors are regular sensors that we're using from commercial companies. And the beauty is that the underground node and the above ground hub are about $200. And we have a small battery, which can last a few years. So a nice solution that can allow us to work in new areas that we couldn't work before. Another example, our lab is focusing also on greenhouse gas emissions from the soil to the atmosphere, mainly from what is happening in the soil. And the way to measure it is by using very expensive gas analyzer like this one, or like a LICO gas analyzer, if you know. And the idea is to put chambers, without going into the specific technique, but there are like two main methods to measure greenhouse gas emissions from soils, from water bodies, doesn't matter, but one of them is the flux chamber. You put a chamber, and what is being on the soil or on the water body, and what is being emitted from the surface is being accumulated in that chamber. And you are measuring what is happening in the chamber, and from the increase in, for example, CO2, you can calculate the flux. Now, the way to measure what is happening in the chamber usually is by taking samples to a gas analyzer or to a GC in the lab. Now, these are very expensive, and because in recent years, CO2 sensors were developed for different purposes than academia, but they are very cheap and very small. This is 3 centimeters. Instead of taking samples, this is a bucket. It's a bit hard to see. This is a water body. This is a bucket from experiments we conducted near San Francisco. Instead of taking samples from the bucket to the gas analyzer or to the lab, now we can actually put the CO2 sensor, because it's cheap and we don't care if something will happen to it, and we can put it inside the chamber and get real-time data. And this is what you can see here. This is CO2 concentrations over time. The green symbols is what we are measuring with our low-cost sensor. This is a $50 sensor. And the orange symbols is what we are validating with the expensive gas analyzer. And without going into the details, you can see that the slopes are pretty much the same, meaning we validated our low-cost system. And this is a lunch box, a regular lunch box, but we're using it because here is all the data logger unit, and we're just protecting it from water. We did the same for methane. Here, less successful because of different reasons, but now we're also trying to validate our methane sensor, and then we'll have a device, a low-cost device, which can measure CO2, methane from water bodies and from soil. And this concept is also, we did some preliminary tests with Dr. Shaked Stein from the Kinneret Laboratory, in which we are testing CO2 emissions from the Salmon Creek coming into the Kinneret. This is an example of one of these devices. So you can see this is the chamber. This is the CO2 sensor. This is a fan just to circulate the air. The reason we have this funny tube is just to make it float, of course. And this is the data logging unit with a small solar panel. And you can see this is a modem, so everything is being recorded and transmitted online. An SD card to back up the data, a battery, and so on. Now, it looks complicated, but once you achieve you validate your system, you can duplicate it with, much faster. And I know it doesn't look like a research-grade equipment, but in the end, once you validate it against a research-grade analyzer, you can do science with it, and you can increase your measurement resolution. So this is one example. Another example is a portable incubation chamber for real-time calculation of microbial activity. In different fields, you're doing incubation experiments in which you're taking soils or whatever you want to test, put it in jars, and then you're measuring what is being accumulated in this chamber. And again, the same concept, you're taking samples from the chamber, either to a gas analyzer or to a GC in your lab. But it's very hard to understand what is happening because it's, of course, how many samples can you take? Once a day, twice a day, once per hour. It's hard to really understand what is happening in real time. But because we are using our local sensor, we can actually put the sensor inside the chamber and then get continuous data each minute, each second, whatever we need. And this is what we did here. You can see a CO2 y-axis and O2 y-axis, and you can see over time. And here we just took the solid lines are soil with a carbon source, and the dotted line are soil without any carbon source. And we can see from time 0, meaning from the time we close the chamber, what is happening inside the chamber. And we were surprised because we have high resolution measurements, because we can use this type of sensors, We're surprised, for example, that the soil without the carbon source is emitting more CO2 in the first 20 hours, and then there is a change. It doesn't matter like what is the science here, but it matters the capabilities. Once you measure them in real time, every second, every minute, whatever you need, inside the chamber, you can really better understand what is happening. And if we are measuring CO2 and O2, meaning what is happening with both of these gases inside the chamber, we can also calculate the respiration rate, which is like the CO2 over O2. And if it's 1, it means that for every molecule of CO2 of oxygen, 1 molecule of CO2 is being consumed. And you can see a ratio of 1, meaning that it's 1 to 1. And the blue line is the soil with the carbon source. The orange is without the carbon source. And we can actually calculate by real measurements what is happening in each moment within the chamber. And this is the device I showed. Same idea. These are our incubation chambers. This is, for example, the oxygen sensor, the CO2 sensor. Each one of them is $50, which in our life is relatively low cost for continuous measurements. And this is our data log in a unit. We put it in a very simple box because we don't care. It's in the lab. It doesn't need to be waterproof. And you can see an SD card, a screen for the user, and different additional things. And everything on a very small battery or connected to the wall. And again, new capabilities. And this has already been not like distributed it, but we are working with several labs in Israel that we supply this type of chambers, and very nice results. We are getting very nice results from different types of experiments. Another example is a portable spectrophotometer for field measurements. We took a research published on a portable spectrophotometer by a different group in Europe. Because it's open source, they provided all the details of how to build it. And then we took it from the lab, installed it, the box you see here, we copied their box, added these are a few pumps. This is soil in the background. And we developed a device that can take water from the soil using a suction cup, take the water, put it in the spectrophotometer, and we can get in real time what is happening with the nitrate in the soil, which was part of my postdoc. And you can see the results. The blue is our system. The red is our validation using lab measurements. And this is nitrate over time. And you can see that the scale is pretty much similar. Of course, it's not a perfect fit. But from this type of validation, we can also quantify the uncertainty or our accuracy. And the beauty in this specific system is that the person developing this system is a high school student from California that approached the lab I was in. And she asked for a project because it was very important for her for her CV to get for an application for Stanford. So she wanted a project that she can publish. And she developed the entire system with my supervision, but it was her work. And I'm showing it because this type of sensors are not necessarily, again, from the academia. It's from people that like to build things in their home or in their own homes, maker community. Because it's also low cost, it doesn't need to be in the US or Europe or Israel. It can be all over the world because the resources are lower, the needed resources. Another example. During my postdoc, I started my postdoc, and a month after COVID came. So there was also weird research that we had to do, but it was we felt like it's important. So I was approached by the San Francisco Opera, approached one of our researchers at UC Davis, and they wanted them to develop a mask that you can sing opera, but still not. But it will still be safe COVID-wise. So they developed the mask. It was something like that, you can see. And they did test, and you could sing opera for a few hours. And it was okay, no one is being infected. But there was a concern that if you're singing inside the mask, maybe there is a CO2 buildup, and maybe it's a health risk to the person using this mask. So they asked me if I can measure the CO2 inside the mask. You cannot do it with regular commercial sensors, they are too big. We took the same sensor I presented before, 3 centimeter, just inserted into the mask, and then we did test with people singing, and you can see it's a bit hard, but the blue line, this is CO2 over time in seconds. The blue line is the CO2 during singing, the red line is during talking, and we can see there is no CO2 buildup. But then they took off the COVID limitations, and no one used this mask, which I'm happy, which is not something you usually say when no one used our product, but that's okay for good reasons. But I'm showing this because it's an example of customized solutions to things that you cannot do with commercial sensors. And of course, I didn't develop this field. I jumped into something that was already happening. There are not a lot, but there are, let's say, at least a few tens of groups in the world, also from the academia, developing different types of sensors for different fields of research. One of them is focusing on the ocean, which there the sensors are very, very expensive because you need to work under high pressure and different challenges. And they are providing designs including 3D printable files, how to build your own sensor to measure electrical conductivity, dissolved oxygen, temperature, pH, and so on. They have a lot about the philosophy, do it yourself, connect to the sea, community. Again, it's a lot about the philosophy, not just about like doing science. And then we took their design and we just tried it in our lab. And now we are working on a device that can measure similar parameters. Everything is in the tube, the data logger, the power. And then you're just taking it into the water and it can sustain a few tens of meters. But we are just at the beginning stage. But another example that you can really lower your cost, and by that you can get more measurement points, because then you can build a few of these and not just one that you need to move it in space. Great, so everything is perfect. Everyone wants their own sensors. So of course it's not that easy, it's challenging. There's a reason why it's only a few tens of groups in the world and not every lab that measures something or using this type of sensors. There are also a few different review papers discussing these issues. This is one of my favorite because it's really talking about the challenges and the opportunities, but focusing on the challenges. And the main ideas or the main challenges is first that, of course, it's not a straightforward process. Like when you buy your own sensor when you buy a sensor from a commercial company, first of all, you have support. Then in a matter of a few hours max, you have something which is working, and there was a fleet of engineers testing it and making sure it's working. When you develop your own system, you need to validate it, you need to waterproof it, you need to test it, you need to do a lot of different stuff that takes time. Time is money. So it's not that easy. I would say that if it's a parameter that you're using in your lab, for example, I'm using a lot of CO2 measurement because this is our field of interest. So we're investing a few months to a few years, depending on the product, to develop a system that can measure CO2 accurate. Once we are done with that, we can duplicate it much faster, and then we have a lot of different measurement points. So it's a long process, but if you do it once, most of the time is for the system number 2, 3, and 4. Of course, the time will be reduced. There is a learning curve. I wouldn't recommend to start with it if you're a researcher or a master's student in your last year. But if you're a PhD student in your first year, or if you're a technician, I think it's a great capability and if it's needed, of course, for your research, I think it's recommended to at least try. And it's fun. Like we're building stuff with our own hands. We're doing something that it's working in the end and give us advantages. And compared to commercial sensors that you buy and you have a nice data sheet that you can really trust, sometimes you get sensor, like you buy something from AliExpress, you don't know what it is, no data sheet, but there are ways to work around it, like buying from better companies or companies with documentation, like the company I showed before, and then you are getting a data sheet with accuracy and so on, and then it makes life a bit easier. So challenges, very significant challenges, but if it's relevant, so it can be a very nice solution. Okay, so until now I talked about sensor. Now I'll show a few examples of what is happening in our lab. And we are focusing on, again, soil-atmosphere interface, coming from the soil perspective, not from the atmosphere. But of course, you cannot differentiate. We build our own sensors in our makerspace in Sde Boker, but we also have high-end systems like eddy covariance, which we just received, and we are getting into this field that you can measure. Our eddy covariance can measure methane, CO2 from relatively large areas, and we have also different gas analyzers. So we're combining both because you cannot do when you're using low-cost sensors, you always need to validate them against something. The first project we are trying to initiate for a year or so, together with also Nadav Lensky. They have a station, this is from Hula Valley, but it's the same station, eddy covariance, a flux tower that can measure CO2 and methane. They have one station in the Kinneret, which of course one station is nice, but it's not giving you the full story. And we want to take this type of chambers. This is a conceptual, let's say, concept. It will not be that this numbers because in the Kinneret it's a bit hard to put chambers because you're very restricted in the location. But let's say 4 chambers, even for a few hours in different locations. And now you can compare fluxes from different places in the Kinneret. And from that, you can understand what is happening, correlate it to atmospheric conditions or whatever your research question is. A big project we are starting now, together also with Alon, in which we are trying to understand how the carbon budget in restored wetlands in Israel. So different PIs from different disciplines, so each one is focusing on a different perspective. We are focusing on sampling, actually seeing what is happening, so the other groups can correlate their insights. And we're just starting, and this is for a 4 to 5 year project, still debatable. And now we finish with our 2 main projects happening in the lab now. The first one is we are trying to quantify and explain the mechanisms controlling CO2 emissions from arid land, okay, arid soil. There is a lot of study, of course, on soils from different locations, Amazon, whatever. But from arid land, no, because it's considered a very low soil in activity, so low CO2 emissions. But there are a few papers from the last few years showing that although it's low, it's very wide in area, the arid soil, so it might make a difference, or at least close a bit of the uncertainty in the different climate models. So we first identified all the mechanisms that are controlling CO2 emissions between the soil and the atmosphere, like of course diffusion, but also thermal convection, wind-induced convection. When wind is blowing over a surface, there is pressure pumping, and also the biotic mechanisms like respiration and the things that you are aware of. So first we identified the concept, and now we're starting to measure in different locations. So same idea of different low-cost sensors, in this case CO2, O2, soil moisture, and data logger, low-cost data logging unit. And instead of putting one eddy covariance, one flux tower to measure an area, we can now, because it's very cheap, we can install in different locations and get a high-resolution data set. And how we are doing that, how we are putting electronics in the soil. So we develop a very simple, stupid device or system, 50 mil Falcon tube, we cut it, we add the white membrane, it's a hydrophobic membrane. This is without the sensor, but we are soldering the sensor inside, putting it inside the enclosure, and now I can put it in the soil, under rain event, irrigation, we don't care. Gas is still getting inside the chamber because it's allow gas to go in, but water not. And the electronic is still can sustain the water, the irrigation. So it's a very simple design, but now we can use these low-cost sensors also for challenging conditions under water stress. And when using this type of systems, we can get these nice data sets. You can see CO2 concentrations using this type of sensors. Over time, this is after we calibrate them using a high-end gas analyzer. We do it once, and then we are analyzing the drift, but we have an algorithm to fix the drift over time of the CO2 sensor. And you can see this line is the line of the atmospheric CO2. If you see now values, dots below this line, meaning the CO2 in the soil is lower than the atmosphere, above the opposite. And this represents efflux, and this is influx. We are seeing that there are times in the day, the blue dots is around midnight, around nighttime, in which CO2 is entering the soil, compared to times in which CO2 is being emitted from the soil. Once you know the CO2 concentrations and you know the soil water content, you can, by an equation that I'm not going into, you can use what is called the gradient method and calculate the flux, the actual flux, because this is what we care. We care about the flux from the soil, not the concentration in most cases. And you can see, you can quantify the fluxes. So these are relatively low fluxes compared to soil here outside or in the north, but on a wide area. So it might make a difference. We're still investigating it. And the idea, because this is a system that costs around $1,000, we can put it in different locations throughout the desert, going from Yatir forest down to places that are hyper-arid. And now we can really understand what is happening, because we have stations in different locations, and not only one station in the middle of the desert. So that's the idea. And this will be the last example I'm showing. So we talked about CO2 emissions from soils, but we are also focusing on CO2 emissions from abandoned boreholes. What is an abandoned borehole? For example, a borehole that Mekorot drilled 10 years ago, 50 years ago, 100 years ago, whoever drilled the borehole. They took the water table is decreasing due to different reasons, and then they are abandoning the borehole because they don't have they don't need it anymore. Of course, they will not fill the borehole, they are just abandoning it, putting a nice fence around it that no one will fall inside. But suddenly, you have to think of it like a straw going into the deep soil. This can be 10 meters, this can be 100 meters. And suddenly, this is the perforated sections. Areas in the soil that didn't see atmospheric values of air, suddenly seeing the atmosphere. So air from the atmosphere can go inside and interact with the air inside the soil at 100 meters, for example. And this is starting to be problematic because here you have sometimes elevated CO2 concentrations, methane, different VOCs. And if one molecule of CO2 this is let's say 100 meters, a molecule of CO2 will be here and then move by diffusion, I don't really care, it's not a big problem. But because of different transport mechanisms, this molecule is being not transported by diffusion, but by advective mechanisms that are much faster. And then the molecule is being emitted faster and more molecules are being emitted, and suddenly this borehole is becoming a hotspot for CO2 emissions. And that's the idea. Different mechanisms can cause advective transport of this air partial to the atmosphere, like thermal convection. If the air inside the borehole, above the water table, or even if there is no water table, if the air is warmer than the atmosphere, unstable conditions, and then density differences, and we have like very similar, of course, to cloud formations, barometric pumpings, and different mechanisms. But how do you measure it? Like, okay, I want to see. So what? Are you coming with gas analyzer and testing what is being emitted here? Or are you doing it for 1 hour a day? Or like, how can you do it when the sensors are so expensive? So we developed a system at UC Davis. This was a side project that I led with my supervisor, Helen Dalke. This is a 50 centimeter. Just like a very simple rod, different sensors, air velocity to measure the velocity of air inside the borehole, CO2, temperature, relative humidity, O2, different sensors. This is a 5 centimeter diameter monitoring well in California. We inserted these sensors to the upper part of the borehole, somewhere here. All the cables are to this nice data logger. And all the system is around $400. So once you install something in $400, again, without the manpower and working hours, you understand you can duplicate it by 10, 20, how many boreholes you want. And these are the time series we are getting for the system I just showed. This is oxygen, CO2, measured air velocity, meaning the velocity of air moving up to the atmosphere, and the temperature. The blue line is the temperature of the water table, and the orange line is the temperature of the atmospheric air, and the black line is what is being measured here, the air temperature being inside the well. And this is 4 days. Now you can see that there are times in which the CO2 is not zero, it's roughly 400, meaning atmospheric concentrations, meaning air going inside the borehole. It's correlating to also oxygen levels of 21%, which is the atmospheric concentration. And also the temperature is roughly equivalent to the temperature in the atmosphere, the orange line. But in a matter of a few minutes to a few hours, suddenly inside the well, the CO2, the air is changing, the concentrations, and now we are reaching CO2 concentrations of 40,000, which is 2 orders of magnitude higher than what we have in the atmosphere. Also, reduction in oxygen. Air velocity is increasing. And this is signal from 3 independent sensors showing that air is now moving very fast from the lower part. This is a 10-meter well in Sacramento, California. We are seeing air is moving very fast in a scale of a few meters per second, highly dense with CO2 and low on oxygen. And if we have the velocity, we have the concentration, and we know the cross-section, we can also quantify the flux. And this is the beauty of this type of system, that you're actually measuring. No models, no nothing. You're measuring what is happening. Of course, after you validate the sensor, and I'm showing you the end figure, but it took a few months to develop something, and you need to do power optimization because it's in the middle of nowhere on a solar panel. But once it's working, you have data sets that you cannot achieve using other sensors, or you can achieve it in like 100,000 shekels, which is not relevant. Okay, I'll skip this due to time, but I'm just showing like same axis. I'm just showing what is controlling these emissions, which is atmospheric changes in atmospheric pressure or temperature changes, but if you want, I can talk about it later in the break. And the idea, because this system is low cost, so this is one field. In this specific field in California, we have 11 monitoring wells, as I showed, and we want to install different systems in different locations in the field. We know the groundwater flow direction. We want to see if it's correlating somehow to the groundwater flow or to different events due to irrigation, due to fertilization, and so on. And recently, there was a paper that showing a new type of sensor that can measure not only CO2, but also methane and N2O, which is low cost but high resolution. And once this will be in the market, and this sensor is still relatively small, we can put one of these sensors inside and not get only the CO2, but the other two interesting greenhouse gases. Okay, and I will finish with a few slides about the main concept. So in our lab, we are focusing on research, but we are also have a focus on developing this type of sensor systems. We call it the Open Digital Environmental Lab. We have solutions to different weather zone measurements of different gases, as I showed, soil moisture, different parameters. Whatever is related to how you log the data, how you communicate it, how you transport it to the cloud, we have solutions for that. Atmospheric measurements, it's something new that we are going into now, but of course, different solutions, if not from our lab, from different labs in the world. Flux chambers I showed in soils and in aquatic settings. In our institute, we also have a lot of bioreactor measurements, desalination, different processes. So we're implementing our sensors in different studies to see what is happening in real life and not by survey sampling. The entire world of drone-based measurements, of course, a big leap in how we are doing science. Not our field of expertise, but a lot of progress is occurring there. And the entire concept of using this type of sensor was published a few years ago in a short communication note in which we are discussing why this type of sensor can be relevant to different environmental studies and why the psychological challenge sometimes is greater than the actual challenge, when I'm saying low cost, you're thinking, it's not good enough. But it's not always the case. Sometimes it is, but it's not always the case. With that, so remember moving from 1 measurement to 10 in the same price, and sometimes with a similar accuracy, not the same, but similar. You don't need to be an electrical engineer. I'm not an engineer. You just need motivation and time. Of course, it's not just. We're all lacking time. And I will ask you, what do you want to build, integrate? If you have ideas, we're always open for collaboration and just for creative ideas. A lot of different, of course, collaborators, mainly from our institute, Oregon State University, and from the Institute Geological, the Israeli Geological. Yeah. And this is our lab. And this is our view from our backyard. It's the Boker. And thank you for your attention.
Questions?
Yes.
Do you teach a class? Can you send Andre to your class?
So I was supposed to start this semester, but Tzav Shimon changed it. But yeah, we're going to teach a class. And we're also working on like a concentrated class of 5 days. I think like a class, a weekly class is better, but we'll offer also a concentrated class, maybe like next year, hopefully. Then, one project and that's it. Yes?
How much software development is needed?
So that's a great question. This type of product, like on a net, when you want to log something on an SD card, it's relatively, if you know to code for data analysis, like simple stuff, you will be okay with that. Always you need to code and upload to the microcontroller or to your data logger. When you're moving into online data sending and server, then it's starting to be complicated. So it really depends on the specific project. But one of the main problems, like once you have a lot of sensors, you're starting to be challenged by the amount of data. How you are, synchronizing all the data and what you're doing with it, because just acquiring data is, we have enough data in the world. Yeah.
So I really like the talk. I like this approach. Something used in the past. I wonder if you can comment on 2 problems I encounter when trying to use this approach. One is when I'm using a few of this cheap sensor, they tend to drift and then have differences between them. So I asked you before. So there's always the challenge of calibrating. Sometimes I use, switching into air, calibrating, or some internal. Otherwise, I found I need to go like every day or 2 to calibrate it. And the other challenge is, it's just when you leave the systems out. So you have problems of vandalism or animals, or how you deal with that.
So the second problem is the easy answer, because we have the same problem with high-end devices, and then like in a $100 system, I care because I need to go to the field to replace it, but it's okay when I'm putting a Campbell Scientific data log and someone steals it, or just win it due to vandalism. It's a bigger problem. And we can install 10 systems, and maybe someone will touch them, and that's okay. We have 10 systems. The accuracy and the drift is the main issue. It's also with high-end sensors. Of course, they are more reliable. We are developing different algorithms to deal with it. For example, the CO2 sensors in the soil I showed, like in the project towards the end I showed. So we started with 1 sensor in the soil, in 1 depth. And we calibrated it in the lab before, put it in the soil. And then we saw it's moving after rain events. And then we said, okay, I know there are algorithms to keep the drift, to lower the drift. So then we read about that algorithm, and then we said, okay, let's put 3 sensors, still low cost, of the same parameter of CO2, 1 next to each other. And it's still low cost because it's $150 for measuring points. It's still 10% of what usually we are buying for a commercial sensor. And these sensors are now at the same depth, measuring the same parameter, but the algorithm is always comparing between the 3. And now we saw that we have a system running for a year. During that year, there was no situation in which all 3 sensors drifted at the same time. So one is drifting, but the 2 other, we are doing averages and different algorithms. The one which is being drifted is always being, like we are correcting it back to the baseline values. But we have places in which we didn't succeed, and we abandoned that approach of using local sensors. It really depends which parameter.
More questions?
Yes.
So I really enjoyed the talk. I think it's an important and a great approach. But one major problem I see with this is that it's knowledge preservation. So you have a master student that does a project, goes away after 2 years. No one documented the device and knows the ins and outs of the device and so forth. And so it would make sense to have more, technicians that sort of stay in the lab for many years, and so you have preservation of knowledge, and they can, rather than working with students that should keep getting the place. So how do you manage a lab like that and preserve knowledge?
So it's one of our biggest challenges. I'm new, so I still don't know, how successful it will be. I hope, I really pushing the students always to document, also the attempts, because it's not first try. So if you change something in the code, as you're doing in every code. And a successful project, in my opinion, ends in a repository in which it's documented, including photos of how you connect, even for the simple person to see and learn. But it's not always working. Sometimes we're not good enough in it. So, yeah. But there are specific journals that you can publish, do-it-yourself guide, and then you also get the academic points for publishing, but also it's been kept for whenever you want. Yes.
You've shown a CO2 flux from arid lands. You said it's slower than more fertile lands. What factor? Factor of 10 or?
So our starting factor of 10 and lower, 10% and lower, then depends what you're comparing to. But if you're talking about general agricultural lands, not after fertilization, but in general, so we're talking about factor to 10, up to 20. But arid soils are very interesting because there are also times in which there is influx. And this is a mechanism which usually doesn't happen in other soils. So there are interesting ways to look at it.
So the negative flux is the carbonate dissolution, I guess. But why is the respiration is so down at night? Because of temperature?
Why is it? What do you mean?
Well, you see net negative flux, and I guess the part that is coming in is carbonate dissolution.
Yes.
But why do you have this diurnal cycle?
Because the decrease in temperature increases the solubility, and then in morning time
Because of dew, so we have more water, or just?
Yeah, it's still debatable. For example, Nurit Agam from our institute thinks it's more related to early morning, they call it non-rainfall inputs, dew, fog, depending on which type of desert. But it's still debatable. Also because no one really tested it, because all the universities with high quality instrumentation are not located near deserts. And then if you want to measure something in a desert which you need to fly to, usually you will not do it or do it very sparse.
More questions? Okay, so thank you very much.
Thank you.